Question 131 is quite the extension of what was introduced in this chapter. It wants you to consider a reaction of H2 plus I2 going to 2HI. Recognizing first that we have an equimolar sample of H2 and I2 allows us to use the second order kinetics for the chemical reaction. We see that, as provided, the rate constant is 2.42 times 10 to the negative 2, 1 over molar second. The units of 1 over molar second tell us that this is second order overall. We could assume first order with respect to each reactant, but if we have equimolar concentrations of both of these, then the rate of change of both of these would be the same, and we could treat this using second order kinetics integrated rate laws. However, in order to use these integrated rate laws, or the integrated rate law for second order kinetics, we need to convert the pressure into a concentration, which will make more sense in using a K value that has units of molarity. When we have a gas, the properties of the gas are governed by the ideal gas law, and if we were to rearrange the equation to solve for moles per volume or moles per liter, we could get a concentration, a molarity associated with that gas. The total pressure is 1658 millimeters of mercury. If we divide that by 760 millimeters of mercury, we will get atmospheres. We can then divide by R, which is 0.08206 liter atmospheres per Kelvin mole, and then the temperature, which is 400 degrees Celsius or 673.15 Kelvin. This allows us to calculate the total concentration of H2 and I2 together at 400 degrees Celsius before the reaction occurs. That is 3.95 times 10 to the negative 2 moles per liter total. Or we could consider each of these, because it's an equimolar mixture, each of these being half of that at 1.97 times 10 to the negative 2 molar per liter, or moles per liter. The rate then will be equal to the rate constant, which was given to us, multiplied by the concentrations of each of the reactants raised to the first power, second order overall, and we get 9.44 times 10 to the negative 6 molar per second. We have units of seconds here, so we're going to have units of seconds here. However, the question needs to be more complicated, so they want it to be in minutes. So we'll convert our seconds into minutes, and we get 5.66 times 10 to the negative 4 molar per minute. So this is the rate at which each of these is decreasing. But HI is increasing at twice that rate. We get 2 HIs every time one of these is consumed. So we need to double that rate in order to express the HI rate of production, which would be 1.13 times 10 to the negative 3 molar per minute. Now for part B, it wants us to determine the rate of formation of HI and its concentration after 10 minutes. Now we need to consider some stoichiometry. As the reaction occurs, we get a decrease in the concentration of H2 and I2 and an increase in the concentration of HI. Because we are considering this a second order reaction, we can use the second order integrated rate law. But now, to do so, we are considering this to be second order as if it has just one reactant, and the one reactant just having the one concentration initially of 1.97 times 10 to the negative 2. So we'll state that for the second order overall, 1 over the concentration of either one of these reactants will be equal at time t minus 1 over the concentration at time 0, which is what we determined up here, will be equal to K multiplied by T. After 10 minutes have passed, 60 seconds have passed. This now allows us to solve for the concentration of one of these and both of them together after 600 seconds or 10 minutes, with this being the initial concentration. With a little bit of algebra and rearrangement to save space, I just went straight to the answer. You'll get a concentration at time t of 1.53 times 10 to the negative 2. But this is the concentration of each of these. If this is 1.53 times 10 to the negative 2, then there must have been this much of a decrease in concentration. The decrease in concentration of each of these corresponds to, or is related to, the increase in concentration of HI. So if we subtract the concentration that we had minus the concentration at time t, this will tell us the change in concentration, which will correspond to the increase in concentration of HI. However, HI is increasing in concentration at twice the rate as each of these are decreasing. So what we have to do is we need to multiply that by 2 to get 8.76 times 10 to the negative 3 molar. That will be the concentration of HI after 10 minutes. What then is the rate after 10 minutes? Well, rate is going to be equal to K multiplied by the concentration squared, or each of these concentrations are the same, so it would just be 1.53 times 10 to the negative 2 times 1.53 times 10 to the negative 2. That gives us 5.66 times 10 to the negative 6, 1 over molar. Molar per second. However, as we recognized up here, this is the rate of decrease of I2 and H2, but the rate of increase of HI is double that. So we're going to double this and also convert our seconds into minutes. So we'll multiply this by 2 and then multiply it by 60. And we'll get the rate of production of HI being 6.80 times 10 to the negative 4 molar per minute.